Welcome all in the SAR data processing lecture 2 of this course. Actually, there is some announcement. The lecture which is scheduled on the 14th April is actually will be held on tomorrow, that is 12th April, and the schedule for that one is actually like that. Tomorrow there will be two classes, like for SAR polarimetry and SAR interferometry. So from 2:30 it will be start the SAR polarimetry lecture, and after that around 4 p.m. There is another lecture, SAR interferometry, because that there is a holiday on the 14th of April, so we have preponed that lecture of SAR interferometry tomorrow. So please join the course tomorrow from 2:30 for the two lectures, SAR polarimetry and SAR interferometry. Okay, and this revised schedule is also uploaded on the website and also in the LMS portal. So yesterday in the lecture of the SAR data processing 1, we have studied about the data processing which is at the raw data. So what are the different algorithms we can do the focusing of the SAR data. Now in today's lecture we will see how to do some of the processing in the level 1 data after the image is formed, means in the focus data level 1 data, what are the corrections we can make and what we can the post processing we can do. So we have different SAR data products actually. So first is the raw data product, which is called the signal level data or the level 0 data. So after doing the raw data processing, we will get the slant range product. Okay, so slant range products are the processed products. So it can be of two types, SLC and SLD. SLC means it is having the complex nature, means it will have the real part and imaginary part, and the single look detected is the amplitude part, means single band image, it will be of like a image. But in the SLC we have the two images, real and imaginary, and there we have to do some formulation like the square root of a real square plus imaginary square to get a image out of it. Third product is the ground range product, means we have to convert this slant range to the ground range data. And the last products are the geocoded products. So we can have the geocoded products like geocoded ellipsoid corrected product and geocoded terrain corrected product. So in this ellipsoid corrected product we can have this used without them. So we can take the height as to average height of the scene to correct the image, and for the geocoded terrain corrected product we have to use the digital elevation model. So how the flow of the different products means, initially we will get the raw data, we will do the signal processing like range Doppler algorithm and focusing algorithm like range compression, azimuth compression, RCM correction. That type of signal processing we have to do to convert that one to from raw data to the single look complex data. So after the image is formed, single look complex data, that is called the level 1 data, we can generate the ground range product, and we can do the some geometrical corrections using the average height, and we can use the digital elevation model to make the image in the terrain corrected product. So how the slant range products are there. So in the slant range product, actually the products are in the actually in the sensor geometry. Sensor geometry means we have the range and azimuth, means pixel direction is the range. So if we have the image, so if we have this type of image, so in this image in this direction we will have the pixel direction, so this is called the range direction, and this is called the azimuth. So in this slant range product, this is in the sensor geometry, it is not in the map geometry, means here we cannot directly take this image to correlate with any other image or Google Earth or Bhuvan, we cannot, because it is not rotated, it is in the sensor geometry. So SAR slant range products are of two types, SLC, which is of two files containing real part and imaginary part, and we have the detected product, means it is called the amplitude or intensity images. And next is the geotagging, means every pixel have the lat long, means we have the information of the lat long, but this lat long is not rotated, so it is in the it is simply in the sensor geometry only. So what is the range pixel size, means what is the size of the pixels, means what is in the meter, how much difference between two pixels. So that is given by the c by 2fs. C by 2fs means c is the speed of light and fs is the sampling frequency. So in the range direction we know what is the sampling frequency, SAR parameter. So if we do this calculation c by 2fs, then we can get the pixel size in the range direction. Okay, so here in the slant range we don't have the square pixel size. The pixel size in the azimuth is different and in the range it is different. So it is not a square pixel size, it is a rectangular pixel. So the geometry in the slant range products is not correct. Okay, so we have to do some geometrical corrections to correct the geometry of the SAR products so that it can be used in any GIS software. So in the slant range detected product, this is the raw data, and after doing some signal processing we are getting the slant range detected product. So in the slant range detected product complex product, which is called the SLC, so you can see the two images. This is called the real part and imaginary part. So this is a process data only, but in the SLC domain, means it is the single look complex image where this is the real part and imaginary part, and this is the amplitude image. Amplitude means it is the square root of real square plus imaginary square. So in you can see in the this real imaginary part we cannot distinguish the features, but as we are doing this amplitude image, then we are able to see the features. So if we are getting any SLC image, so we have to do some calculation by doing this square root of real square plus imaginary square to get a amplitude out of it to see the features. Next is the slant range product. Slant range product is the SAR can image both in the ascending node and the descending node. So SAR can look in both right and left direction. So in this image you can see if this is SAR, so it can look in the left direction also, and it can look in the right direction also, and it can acquire the in the ascending node and descending node data also. So when the satellite is passing from the north to the south, then this is the descending pass, and when from south to north pole, then it is a ascending pass. So normally the optical satellite if it is sensing near India, so most of the descending data descending pass data we are acquiring, but in the SAR we can acquire the data in the ascending pass and the descending pass, because it is not dependent on sun, because in the descending pass it will be a daytime, so we can acquire the data in the daytime also, and in the ascending pass it is a night time, and SAR can image in the night also, so we can have both ascending and descending data. So in the slant range product, actually we can have some flipping in the actually in the features. So if you can see, if this is an image, actual earth surface, and this is the range direction and this is the azimuth direction. So if it is a ascending right, means the sensor is moving in this direction ascending, and it is looking right. So you can see this image, in this image this part will image first. Okay, sorry, this part will image first, so it will come in the top. Okay, because this is the ascending right, so it is looking in this direction, so this part will image first and it is right at the top. Okay, so there will be the azimuth flipped. Okay, so in this direction you can see in the azimuth direction there is a flipping. Now second, if it is a ascending left, means if it is going in this direction and looking this, so you can see this image, it will image first, so this part will come in the first pixel. Okay, so there will be the range and azimuth both side flipped. So original image is like this, but if the data is acquired in ascending in the left mode, then there is flipping in both range and azimuth direction. And if it is in the ascending right, then it is flipped in the azimuth direction. If it is the descending left, so there will be no flip. Okay, so this is the image. So you can see there will be no flip in the image. But if you can see in the descending right, means if you are going in this way and you are seeing in this way, so you can see this this part is will image first, so this is written first. So in the slant range product, we can see there will be a flipping in the range direction and azimuth direction both, because data is actually imaged first if it is the ascending mode and or in the descending mode. So this is the some products in the slant range. Now second is the ground range. Okay, so what is the difference between the slant and the ground range? So slant range is the straight line distance between the SAR and the object. So if you can see, this is the position of the SAR and this is the object, so this distance is called the slant range. Now what is the ground range? Ground range is the distance between the horizontal distance between SAR and object. So that is the this horizontal distance from the nadir to this one. So this is the ground range. So what we have to do, we have to project this slant range into this ground range. Okay, because actually all the processing in the SLC data we will do in the slant plane. It is called the zero Doppler plane. So all these features are coming in the slant range. So we can we have to project the data from the slant range to ground range. So the slant range pixel size, as I already told, it is given by C by 2fs, but the ground range pixel size, it is given by C by 2fs upon sine of incidence angle. So it is a function of the incident angle. Okay, so the we will convert slant to ground by using this formulation. We know the incidence angle, we know the sampling frequency. With the help of these two parameters, we can convert from slant to ground range. So SAR can be presented in either the slant or the ground range. Slant range is the natural SAR range observation coordinate, but the ground range is the slant range projected onto the earth. So ground range is the if we project this slant range onto the earth, then it is the ground range. So the imaging geometry is in ground range. It has the square pixel size. Okay, so in the ground range product, we will try to make the pixel size of the image as a square. So the ground range pixel size is given by C by 2fs sine of incidence angle, and it is also geotagged. So you can see the difference between the slant and the ground range. So you can see this is the slant range product. So there you can see there is a compression in the data because it is not in the square pixel size. Okay, so every image, every feature you can see, it is like a compressed image. Okay, so it depends on the what is the incident angle. If it is the incident angle is lower, then there will be more compression. If the incidence angle is high, there will be a lesser compression. So this now we can convert this slant range to the ground range by using this formulation and make the square pixel size. So in this image you can see it is a proper image. So the features are now proper. It is a square pixel size. So we can do the image interpretation in the ground range better as compared to the slant range. Now you can see this is the basic geometrical corrections, means, and although we have the very much geometrical distortions in the SAR image, so one of the method of the simple thing we can do in the geometrical correction, we can do like simple ground range conversion, and we can make the geometry correct by doing the pixel size like C by 2fs sine theta. Next is the SAR geolocation. So what is the geolocation? Geolocation is the calculation of the geographical coordinates of a image pixel. Radar measures the range from the sensor to the target. A synthetic aperture radar additionally measures the Doppler history of the all return targets. This makes it possible to construct a rigorous sensor model to geolocate the pixel position on Earth. No onboard attitude is required for the geolocation for the SAR case. So actually in the SAR we have the range and we have the Doppler. So with the help of this range and Doppler, we can make a sensor model and we can geolocate any pixel. And in case of optical, where we will use the roll, pitch, yaw and interior and exterior orientation for the geolocation. But in case of SAR, because we use Doppler to focus the image, so we are getting very accurate Doppler value. Okay, so we can get a very much very accurate range value and very accurate Doppler value, because if these two things are not accurate, the image is not focused. Okay, so if the image is focused, and then the range and Doppler are very much accurate. So for this accurate range and Doppler, we can use these equations to geolocate any feature of an image of a synthetic aperture radar. So accurate Doppler is estimated from the image needed for the SAR image focusing. This attitude information essential for the optical sensor geolocation, and optical geolocation accuracy depends on the attitude accuracy. So in the optical, actually we are dependent on the attitude information, means we have to calculate this roll, pitch and yaw. So this roll, pitch and yaw accuracy is dependent on the dependent on the instrument accuracy. So how much accuracy of the roll, pitch, yaw, that accuracy will reflect in the geolocation. Okay, so if the roll, pitch, yaw are not accurate, then the geolocation accuracy will degrade. Okay, but in the SAR we can have, if the range and Doppler and the orbit is very much accurate, then we are getting a very accurate geolocation. So what is the SAR geolocation? Like this is the geolocation is the process of calculation of the geographical coordinates of an image pixel. Okay, so for this image, what is the lat long we have to find out. So this is the for a particular pixel we have to find out the lat long. So in the SAR geolocation, the location of an arbitrary pixel in a SAR image is determined by the intersection of radar beam with the planetary surface. So we can have this Doppler equation, which is a Doppler cone, and the range equation. That is it is a type of sphere equation, and we have a model of the Earth. So we have three equations. One is the Doppler equation, one is the range equation, and one is the ellipsoid equation of the Earth. With these three equations, we will solve these three equations to geolocate any point in the image. So in the SAR geolocation, we have three equations. One is the Earth model equation, SAR range equation, and SAR Doppler equation. So we know the satellite state vector, means we know the time and everything about the satellite. We know this range information from this one, and Doppler information. So where it will intersect on the ground, so we have this Earth equation also. So these three equations, where it is intersecting, we can find out this x, y, z. So here you can see, if this is a platform, so this is the Earth and there is the radar beam. So where it is intersecting with the Earth surface, that point actually we can geolocate. So here this is the concentric circles we are happening, and this is the hyperbolic equation. So this is the Doppler lines, and this is the lines of equidistance, which is called the concentric circles. So we can have the intersection of this circles and this hyperbola with the Earth. So this intersection of all these 3 points, 3 equations will give a one unique point. So this unique point is the location of a target. Okay, so that in that way we can geolocate any pixel on the ground. Okay, so after doing this SAR geolocation, we can do this approach by two ways. One is the image to ground geolocation and second is the ground to image geolocation. So when we are doing image to ground geolocation, that is called the forward geolocation. Like for any scan and pixel index, means in a SAR image, if we have I and j, so for a particular ij we have to calculate that lat long. Okay, so we are modeling in such a way in a forward geolocation, like for any pixel we have to find the lat long. Okay, so this is called the forward geolocation. Second is ground to image geolocation, but this is called the backward geolocation. So for that one we will have one ground, means in the ground we have the information of lat long, and from there we have to see in the image what is the ij. So we have the reverse mapping for a particular lat long, what is the ij in the SAR image. So that is both is using the range Doppler equation, but the parameter is different. From here in the forward we are estimating from ij to lat long, and from ground to image geolocation from lat long to ij we are calculating. So based on this SAR geolocation, we can convert our SLC image to the geometrically corrected image. So what is two type of correction? We can do the geocoded ellipsoid correction and geocoded terrain correction. So as I already told, like in the this image, it is in the map geometry, so it is not in the map geometry. Okay, like lat long wise it is not rotated, means we cannot do any GIS application here. So for that we have to do, or we have to convert this image into the map geometry. So how to convert? So there are two methods. First we have to attach the ij to the lat long, means for particular ij we are doing this process of geolocation, like we are tagging a particular pixel with a latitude and longitude, and then we can use either the average height or digital elevation models to make or to convert from the sensor geometry to the map geometry. So in the geocoded ellipsoid correction, we are using the earth surface as a smooth ellipsoid surface and useful for the areas where surface is flat or dams are not available. Okay, if the area is very much flat and dam is not available, then we can apply this ellipsoid correction. So in this correction it is actually assumed like a average height of particular scene. We are not getting a height of in every pixel. Here we are considering every pixel have a same height, and then we can convert, we can do some geometrical corrections. And second is the geocoded terrain correction. In this one it is also called the ortho rectification, where what we will use the digital elevation model to correct the geometry of the SAR. Okay, so this is the more precise product, and we can overlay this image, ortho rectified image, to any other image. Like if we have the optical image or hyperspectral or multispectral image, then we can just overlay this SAR image over the optical images if it is the orthorectified. The GEC image also have some geolocation inaccuracies because it is not using the height for every pixel, and this slant range is always a geometry is not correct. Okay, so if you want to do the correct analysis based on the map or based on any other optical satellite, then we have to convert this slant range product either in the GEC product, which is the ellipsoid corrected product, or we can use the GTC, or it is called the terrain corrected product. So these are the basic processing which is called the level 1 processing in the SAR image we have to do, because we can do analysis in the SLC image, in the phase image, but for the proper for comparing the SAR image with other images, we have to do the geometrical corrections in the SAR image. So the SAR geocoding can be done either using the geolocation grid or the range Doppler model itself. So in the GEC we can use the average height, which is called the geocoded ellipsoid correction, and in the GTC we have to use the digital elevation model, which is called the DEM. So in the SAR geocoding, what we have to do, this is the actually the input space slant range image actually. So from there in the range Doppler geometry, we have to find the like for a particular lat long or ij where it is in the output space. Okay, so this is the in the map geometry, mean northing or easting, or it can be a latitude or longitude domain. So that is the output space, and this is the sensor geometry. So from sensor geometry, from this ij we have to go to the lat long geometry. So this actually is done through geolocation. We know this mapping from the either this ij and lat long. So what we will do this one, and we will put this pixel here, and we will do some resampling like NN nearest neighbor or cubic convolution to resample the data or to write the data, because when we doing the mapping, so it is an integer number, but output number cannot be an integer, it can be a decimal value. So for mapping the decimal values, we can use any interpolation method like nearest neighbor or cubic convolution for converting the slant range to the geocoded products. Okay, so this is the basic principle of SAR geocoding, means we have to convert the image from slant range geometry to the map geometry. Okay, now what is the geocoded ellipsoid correction using geolocation grid? Actually in the geolocation grid, what it will be happen, we will generate the lat long of each range and azimuth value or pixel scan using the forward geolocation at each interval, assuming the average height. Okay, means we have the image, and for particular image at particular pixel scan, we will calculate the lat long using the forward geolocation model. Okay, so from there we will find out for a particular pixel value what is the lat long. So this type of grid we can make, like for a particular pixel what is the lat long, and for that what we will do, we will using this geolocation grid, we will use some polynomial fitting to convert from slant range to the geocoded ellipsoid corrected product. Okay, so in the output space, corresponding scan pixel in the input space is computed using the polynomial fitting. So for grid like, we can find out at every 10 cross 10 or 32 cross 32, like that we can find out grid, means after every 10th pixel we will find this lat long, and we know the for particular grid points what is the lat long, and in between points are interpolated using the polynomial fitting. Okay, so after doing this one, we can use the geocoded ellipsoid corrected products for our other application. So you can see this image, this is the EOS 4 slant range image of Dehradun area. So in this image you can see this is the somewhat you can see the geometry is inverted. Okay, so you can see this is the this portion is coming first, actually this actual image is this, and in the slant range geometry while acquisition it is acquired here. Okay, so you are seeing there is a flipping in the azimuth direction. So in the slant range there will be the flipping, and there will be flipping in the range or azimuth direction based on the ascending or descending or right or left look data. So if this is the image, then we can apply the geocoded ellipsoid correction for mapping of this I and j. So you can see this is the image, and by doing the geocoded ellipsoid correction, the image is rotated. Now this image is in the geographical plane. Okay, so it is the rotated because our orbit is not a like a polar orbit, it is sun synchronous orbit, so it is somewhat inclined. So our image is also inclined due to the inclination of the orbit. So this is the actual L1 data which is in the sensor geometry. This is the range and azimuth, but with the help of the SAR geolocation and ellipsoid correction using the average height, we have converted this slant range to the geocoded ellipsoid corrected product. So this image have the lat long, but you can see these features. This is the mountainous region, it is not corrected actually, so it is appearing as it is. Okay, so we are not using the actual height of the terrain. Okay, so here average height is taken, so it may have some geolocation inaccuracies because we have not consider the digital elevation model here. So to make a proper image or proper terrain corrected product, we have to use the digital elevation model. So you can see in this image, so this is the EOS slant range image. So this FRI region, so you can see this is the FRI. So it is in the slant range image. It is the now after the geocoded ellipsoid correction, the geometry is corrected. Okay, so you can see now it is properly geometrically correct, but there will be maybe shift in the azimuth and range direction due to the because we are not using the height here. Okay, so now we can see the different concepts of the SAR geometrical distortions. Okay, so first is the relief displacement. So what is the relief displacement? Due to the different imaging geometries of SAR and optical systems, topographic displacement differs between the systems. Horizontal displacement of the SAR sensor is highest near nadir and decreases with the incident angle. Horizontal displacement can be severe at the small incidence angle. In contrast, topographic displacement for optical systems increases with increased incident angle. So that the relief displacement is happening in both SAR and optical. But in SAR, this relief displacement is very much higher as compared to the optical case. Okay, and in the near nadir, there will be more displacement as compared to the far range. So what is the actually the difference? Because the displacement in the optical image, it is given by the h tan theta, and displacement in the SAR, it is given by formula h cot theta. So let us calculate how much is the displacement in SAR and optical sensor. So you can see in this image, so this is the optical sensor and this is a SAR sensor. So in the optical, if we have some if we don't have the nadir looking, if we have the angle like 0, 10, 20, 30, 40, 45, so how much is the s tan theta? It is going from 0 to 100 meter maximum for a 100 meter height. Okay, so we are just having the 100 meter height. This h is the height of 100 meter. So how much displacement? This d displacement is there. So it is like 18 for 10 meter height, it is 18 meter, 20 meter height, it is 36 meter, and 30 meter height, it is a 58 meter. Now in case of optical, we can see for different angle like from 10 to say 50 degree. So at the 10 degree itself, we have very much higher displacement, which is around 567 meter. So for a 100 meter, we are having the around 500 meter displacement. So in case of SAR, because at low angle itself, it is having very much high relief displacement, so there will be more geometrical distortions in the SAR as compared to the optical because of the formula of s tan theta and h cot theta. Okay, so what are the different distortions due to this relief displacement? There will be different distortions in the SAR. So there are three major distortions. One is called the foreshortening, second is called the layover, and third is called the shadow. So what is the foreshortening? So foreshortening, actually you can see in this figure, this is the mountain. So this is the mountain, this is A and B points. So actually what it will do, because SAR is a ranging sensor, so it will have the different ranges. Okay, so this feature is actually compressed in the slant range image. Okay, so this is the A dash, you can see A and B, this point is, and this length is actually compressed to somewhat this length. So foreshortening is the appearance of compression in topographic feature in the scene. Features appear to be tilted towards the radar. Foreshortening is maximum when a steep slope is orthogonal to the radar beam. So you can see this is the optical image, some mountain is there, and this is the slant range image. So this actually you can see this very much bright returns, this is very much bright returns. So this feature, actually this mountain feature, actually it is compressed. Due to this compression, the pixel values is very much increased, because there is a compression and there is a accumulation of the DN values. So it will result a very much brighter this feature in the bottom of the mountain. This is called the foreshortening. Okay, so in the slant range image, this foreshortening will appear like this one. Once we do the ortho rectification, which I will do, I will tell you later, so it will correct it like this one. So if you have the slant range product, the foreshortening will happen, will be seen like this way. But if you have the terrain corrected image, then the foreshortening will be look like this one, because it is spread, because we are using them and we are correcting the position, so it is looking like this one. So if we are analyzing any image, so we have to see it, either it is a slant range or it is a terrain corrected. If it is a slant range, then the geometrical distortions like foreshortening will appear like this one. But if we are analyzing the ortho rectified product or terrain corrected product, then this distortion will appear like this one. Okay, so this is the naturally it is coming like that one in the image, but with the help of this geolocation, geocoded terrain correction, and with the help of digital elevation model, we are doing this type of thing to position the pixel at a correct position. Okay, so this is the foreshortening. Second is the layover. Now layover is the extreme case of foreshortening and occurs when the incident angle is smaller than the local slope. So when this is the when SAR is acquiring this one, so you can see, because SAR is an ranging device, so you can see in this case this B range is lesser and A range is larger. Okay, if this is a mountain and it is so you can see this B point will image first. Okay, because SAR is a ranging device, so it has the shorter range. So which range is short, it will write first. So you can see this B will write first and A dash will write second. So there is the actually the inversion of the geometrical feature. So that is actually called the layover. That is means in the layover, the reflected energy from the upper portion of a feature is received before the return from the lower portion of the feature. In this case, the top of the feature will be displaced or laid over relative to its base when it is processed into an image. So it is laid over towards the radar sensor. So and this is called the one is foreshortening. This is called the compression of the mountains, and second is the layover, where the feature top of the mountain will come first and the base will come afterwards. And third is the shadow. In the shadow, actually where the radar energy not going. So if it is, you can see, and this is the object, so there actually in this region we are getting no return. Okay, so that is called the radar shadow. Okay, so that shadow is not of a sun shadow, it is because SAR is an active sensor. So where the energy means where the backscatter is not coming from, so that portions are called the radar shadows. Okay, so radar shadow indicates areas on the ground not illuminated by SAR because of the viewing geometry and scene relief. Since no return signal is received, radar shadow appears very dark in tone in this imagery. SAR shadow is most common in steep terrain image at the large incident angle. So you can see the different layover, shadow and foreshortening from near to far. So if you are seeing this one, so you can see the layover will happen more in the near range. Okay, so you can see that if this is the top and this is the bottom, then top will come first and bottom will come later. So this layover region is larger. So as we are going from near to the far, this layover will start decreasing. Okay, so, and this shadow will start increasing. So as we are going from near to far, so we can have the different layover and shadow conditions. So you can see in the far range we have the more shadow, and in the near range we have more layover. So if you want to avoid the layover, so we have to do the in between imaging, like from 40 to 45 degree. If we are imaging, then we are getting the less layover, okay, and shadow will be more. If we are having the 10 degree or 20 degree, then the layover will very much, there will be no shadows. So it is your if it is your as per your analysis, if you want to target any area in the terrain, if you want to see any terrain, so you have to see where it is going. It is coming towards the layover region or in the shadow region. If the any feature is coming in the layover region, then you have to increase your incident angle. Okay, if your feature or any target is coming in the shadow region, then you have to decrease your look angle. So it depends on, means if your scene is or your feature is not coming in properly in the SAR image, so you have to adjust with the look angle of a radar. Okay, so you have to either increase or decrease the look angle to actually acquire the proper feature in a SAR image. So this is the you can see here this figure also define the layover, foreshortening and shadow. So in this figure you can see there is first there will be a layover. So this A and B we are seeing, this is B dash and A dash, there is having a layover, and in the C D we are having the foreshortening, and here in the DE we are having the shadow portion. So these are the different distortions in a SAR image which is called the layover, shadow and the foreshortening. So in this you can see this is the one image. You can see this is the actually the top of the mountain, but this top of the mountain, when we have grabbed this image on the dam, so this is the only geocoded image, not the terrain corrected image. So in the geocoded image you can see this top of the mountain is actually have come before, so it is not at the correct position, so it should be at this position. Okay, but due to the layover it is coming here. Okay, so we have not used the digital elevation model, so it is not correctly placed actually. So after using the terrain correction, we can correct the position of this mountain correctly. Okay, so how we can do this is done through the geocoded terrain correction using the range Doppler equation. Okay, so this algorithm solves the range and Doppler equation to determine the range and azimuth position corresponding to the position in the px, py, pz on the earth. So what we will do, we will do the backward geolocation algorithm. We will take the digital elevation model. So in the digital elevation model we have all the three things: latitude, longitude and height. For this point we will see this point where it is appearing in the SAR image, and that SAR pixel is written in the output space. Okay, so in the case of terrain correction, we will use this sensor modeling and digital elevation model, and as well as of SAR orbit to correct the geolocation of a point and to correct the geometrical distortions which are induced due to the terrain. So in this you can see this is the slant range image, and this is the geocoded terrain corrected product. So here you can see now this mountains, so which is have no proper geometry. So you can now see after the geocoded terrain correction, the proper actually it is perception is corrected actually. So you can see these mountains are looking like a mountains only in the SAR image also, but here you can see due to the geometrical distortion the shape of the mountains is not correct. Now if we are using the digital elevation model and we are using our range Doppler model and sensor model, and we are putting a particular pixel at a particular correct lat long, here the mapping is done from the from the sensor geometry to the map geometry, then we can see this is the very accurate ortho rectified product. So this is the EOS SAR image only. So this is the slant range image, and this is the image after the terrain correction. Okay, so this is also called the ortho rectified image. So you can see this is the image when we have done the average height, means we have not used the digital elevation model. So although it has converted to the map geometry, but actually it is not corrected the shape of the mountains, and there will be some geolocation inaccuracies also. But here you can see after the terrain correction proper mountains are formed by using the digital elevation model and the rigorous sensor model and them to correct the SAR image. So you have to see any SAR sensor, either it is a Reset 1A EOS 4 or Pulsar or Sentinel-1, different SAR sensors are there. So what products you are using? You are using the slant range product, ground range product, or terrain corrected product. So if you have to do some analysis, so you have to project your analysis in the correct GIS environment. So you have to do the ortho rectification to your image. Although you can do any processing in the SLC image itself, means if you have the polarimetric image or the interferometric image, you can do processing in the SLC image itself. But after doing all the processing, we have to convert our results into the terrain corrected products. We have to orient our all these results in the proper map geometry, so that we can relate our analysis with other SAR imagery or other optical imagery or any other GIS software we can use for further application. So here you can see this is the EOS product after draping the image on the dam. So this is a 3D visualization. So what we have done, just we have done the terrain correction, and then we have just put our overlaid on the dam. So you can see this is all these pixels values, this all force shortening and layover is spread over the hills. Okay, so why it is happening? Because we are using the terrain correction, we are putting these pixels to a particular pixels. So proper you can see the proper mountains shapes it is coming. Okay, so you can see the comparisons. This is our pulsar image, this mountain, and here actually it is coming in this here the mountain top, but after the GTC correction, terrain correction, the proper it is coming at the top of the mountain. Okay, so this is another 3D visualization of the this geocoded terrain corrected product. This is a pulsar image, and another this is also the slant range image, and this is a GTC product for NOVA SAR 1 S-band satellite. So there we have, because most of the Nova SAR products are available in the either in the slant range and the ground range. So we have done some terrain corrections in the Nova SAR image itself. So you can see after the corrections, these mountains are coming in the proper geometry. And if you can refer this article also, it is published in the GeoCarto International, and for the further literature. Now last step is the SAR calibration. Okay, so what I have told you, like we have done the geometrical corrections, but all these things is in the dn values. Okay, so it is in the digital numbers. Okay, not in the actual backscatter value. Okay, so actual backscatter means we have to find out the energy, because what it will happen, SAR backscatter is observed by the SAR sensor, and then it is converted to the digital numbers. So in an image, the backscatter energy is coming as a dn values. Now converting the dn values to actual backscatter value, so we have to do some calibration. So for that, every SAR sensor will give some calibration constant, which is the sigma naught or beta naught values. So we can generate and we can convert that dn values to the backscatter value by using this calibration constant. Okay, so how this dn values is related to the beta naught? So what is the beta naught product? The radar brightness beta naught is derived from the image pixel values or digital numbers by applying the calibration factor ks. So that is applied on the actually on the slant range image itself. So beta naught is given by the ks dn square. Ks is the calibration constant. So if we will do in the log scale, so log scale is 10 log 10. So in this 10 log 10, we will find out this, it is in the decibel. In the decibel, it is in the 10 log 10 scale. So we can find out the beta naught dB, it is given by the 20 log 10 dn plus k. Okay, so this is how we can convert our dn to the beta naught product. So we know the image dn value, and the calibration constant actually is actually given in the SAR meta file. How it is derived? Actually, we will deploy the corner reflectors, and for that corner reflectors we know the original backscatter, and from dn we will correlate with this value and we can find out this calibration constant. So this calibration constant is provided in the meta file, and this calibration constant we can use to convert the dn to the beta naught product. So basically in the SAR calibration we can generate the three product. One is the beta naught product, and one is sigma naught, and another is the gamma naught. Now in the sigma naught product, it is actually what we will do, it is done if we are assuming as a ground range image. So there we will, the relationship between the sigma naught and beta naught is sigma naught is equals to beta naught into the sine of theta of local incident angle. So if we will have the beta naught, we can convert to the sigma naught in the ground range itself, so by applying the sine theta factor. And the gamma naught, what we will do, it is the gamma naught is equals to sigma naught by cos of local incident angle. Okay, so these three things we can generate from the dn product. So how we can calculate the sigma naught? Sigma naught product, actually it is given by the beta naught plus 10 log 10 of sine of this. So once we are deriving this beta naught product, then beta naught we can calculate the sigma naught product from the beta naught by using the calibration constant. So this calibration constant it is given in the file. We can generate the beta naught, and by multiplying with the sine theta factor we can convert it into the sigma naught product. It is in the ground range geometry. And for the gamma naught, we can we have to divide the sigma naught product with the cos theta, okay, or beta naught product into the tan theta, that can be converted. So with the beta naught we can just convert the sigma naught and gamma naught product, and that actual value will be range in this value. So here you can see this is the slant range product and this is the calibrated dB product. Here you can see normally the range of the DN product, it is positive numbers, but in the DB we can have the negative numbers also. Okay, because our SAR values can go negative also, because in the forest we have minus 10 vegetation, minus 10 dB, minus 15 dB. So once we are doing the calibration, then our values can go in the negative scale also. Okay, by converting. So this is the range. It is like from plus for 50 dB to around minus 22, where water body is also very much negative value, and point targets, vehicle, ships are very much higher values, plus 50 dB. Okay, so these in this way we can convert the our DN products to the calibrated product. So now I will discuss some EOS products. So as I already told you, the EOS product, so we have different imaging modes. So in this different imaging modes, we have the FRS1 mode, FRS2, MRS, CRS and HRS. So we have the level 0 product, okay, and level 1, which is called the SLC product, and we have the ground range, which have the COs and GeoTIFF, and level 2, which is called the terrain corrected product, enhanced terrain corrected product, that also can be down we can get. So we have the raw data, we have the SLC data, slant range products, we have the ground data, and we have the terrain corrected products also. And this COS is the Committee on Earth Observation Satellite, so it has the particular format. So and the data, actually raw data, is basically available in the COS format, but in the SLC data, FRS and FRS2 is available in both COS and GeoTIFF, and MRS, CRS, HRS is available in GeoTIFF, and this different products like L0, SLC, ground range is available for different modes, and all these products is available at Bhunidhi site, bhunidhi.nrsc.gov.in. So what is the level 0? I have already told. Level 0 is the raw data product, level 1 is the geotech product, in which SLC product it is given, and level 1B is the ground range product, which is slant range to the ground range we have converted, and the level 2 products is the EOS for enhanced terrain georeference product, which is the GTC, terrain corrected product, in which DAM is used to correct the geometrical distortions of the SAR. So you can either of the this product you can order. So if you want to do some simple analysis of the object detection and that one, where the phase is not important, then we can use the level 2 product directly. But for the polarimetric and interferometric application where the phase is required, we have to use the SLC images, level 1 images. Okay, so that is as per your requirement. You have to use SLC image or level 2 image as per your requirement. Okay, so all level of products are available in single, dual and the circular polarization for FRS1, MRS, CRS, HRS and FRS2 mode. Quad pole will be operational for FRS and FRS2 modes, and experimental for ScanSAR, and football is not available in HRS mode. So we are having the COs for product also. COs, what is the COs product? It is the consisting of 4 files containing various records. Like in the COs we have the 4 files. One is called the data file, one is the leader file and volume directory file, and this is the null volume directory file. So these 4 files have some formats which is available. So according to that format we can read the data. So this is the SAR. This file will contain the image and image information, it will contain the parameter information, and other will give some supplementary informations. So this COS format is actually different for different satellites, so we have to use the format to read that product. So in the EOS data product we have the image file. First in the it is containing the image file which is available in GeoTIFF product and the COS product, okay, for each polarization. Okay, So this is containing the image like a TIFF file. So you just open this TIFF file as a GOT product, or it can be available in the COS product. Okay, so COS product, it will available like this 4 files. So you have to order your L1 or L2 data, what product you want. So mostly GOT product is available. So here you can see in this table, for that one GOTIF and COS both are available. So here both COS and GOTIF available. Here GOTIF is available for this mode. So you have to choose which data you have to order. Apart from the image, we have one product XML file also, which is containing the several information of the parameter file, and one is the band meta file is also there, which is the containing the ASCII information of different parameters. Another is the git files. The git files is actually it is of like a lat long file. So for each git there is the latitude, longitude, slant range and incident angle. And we have the JPEG image also in the data products, that is the thumbnail of that image. So in a particular EOS data format, we have the two, like if it is a hybrid polarimetry, we have the two files like RH and RV. Okay, so we can have the image files in these folders. This JPEG image is actually the thumbnail files, and this is the git files. We have this git files are there, which is containing the ASCII information in the text file type of thing. Different parameters are there, and this is the parameter file, and this is also one XML file containing different parameters like orbit file, and different SAR parameters are there. So we can see different EOS products here. Here you can see different images. So I will show one by one. This is the Mumbai area. So you can see this image in the slant range geometry, and how this image is looking in the terrain corrected image. Okay, so you can see the mountains here, small mountains here, and water body is there. Okay, so you can see how terrain correction has been done here in the mountains, and this is the brighter portion is actually the geometrical correction, and these are the brighter portion here, it is the urban building, urban regions. Okay, and this is a ship. So this is the terrain this is the slant range image, and this is terrain corrected image, and this is the image, this is the actual resolution, 3 meter resolution. You can see the ships of the US terrain corrected image. This is another image of Chilka Lake. You can see this is the slant range image, and this is the terrain corrected image. So here you can see the brighter things, vegetations, and one here this is the ocean, and here is the lake. Okay, this side it is an ocean, and this is the lake is there. Chilka Lake is there, and this is actually in the original resolution. So this is the original resolution, 3 meter. You can see the land areas and the water, and some nets are, fishing nets are there. Okay, so some brighter portion is appearing in the SAR image. So this is the Kolkata region. So this is in the slant range plane, and this is in the terrain corrected image. So you can see this is the image, this is the actual resolution. So this is the full scene it is covering, and this is the actual region of the Kolkata 3 meter resolution terrain corrected image of the EOS4. And this is the Ahmedabad region. This is a full image, and this is the terrain corrected image, and this portion you can see this is called the Kankaria Lake. Okay, so this is a lake, and this is the urban settlements are there. Okay, so these are some of the products of the SAR of EOS4. So now I can stop here, and I will just show you one sample product here, a sample data. So you can see this is a level 1 data. This is the level 2 data. Actually you can see this here that these two folders are the RH and RV. So this is the TIFF file which is containing the image. Okay, so you can open this level 2 data with any any software like QGIS. Also you can open this TIFF file. Okay, and this are the grid file, level 2 grid file. So here you can see this is the latitude, longitude values and grid values, and here you can see the band meta file. So here it is having the product ID, and you can see have the date of pass, okay, and orbit number, sample number, resolution. Okay, so different parameters you can see the product lat long values also. So different parameters is available as a text file also. So this is the file, and this is the XML file which can be actually can be read using this. Here you can just open different parameters. You can see different parameters of the SAR using this product XML. So these are the some one of the product, level 2 product of the US4 satellite. And how you can order the satellite, I will tell you that part in my subsequent lectures, and maybe in the at the last I will tell you. Maybe in tomorrow's lecture I will show you the Bhunidhi portal, how we can just go to the portal and download the data and order the data. So there these are price, some price is there. You can just go to the Bhunidhi and make a login, and you can just order the data from the NRSC website. So